Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay.
I think the audience.
We actually have the room until 2 noon. That doesn't mean that you should take the whole time, but if you run over, it's not a problem. I'm just going to take this out of it.
Let's get started. So it's my pleasure to welcome Walid Tada from Rice University. He's a professor at Rice, and he's going to talk to us about some work that he's been doing on improving macros, which is an area you don't sort of think of anymore, but I think is actually an area that's it's time to rediscover it and have some better macro facilities in our languages.
Thank you. So what I'll talk about today specifically is some work that I've done on modeling calculi for macros in such a way that they incorporate some ideas that were developed in a very related but slightly different setting of multi-stage languages. And the interesting thing about doing this work from our point of view is that it took these abstract ideas that we had difficulty trying to explain to other people and put them in this much more familiar context where I think they make a little bit more sense. So, where do macros come from? They're not something that, as a language designer, you see a lot of people advocating, but they are things that you find people using, and almost all mainstream programming languages, you find that they support some kind of macro mechanism or the other for practical reasons, because real users of these languages find that they need to have some kind of facility that tends to be called a macro facility. They support things like inlining and for basic values, and especially also for functions or function definitions. The main use for macros tends to be there are two different things. One is to increase, to change the performance characteristics of your program, generally to improve. The programmer would use a macro to improve the performance of a particular program. The other is to also increase the expressivity. Right? And those are different, fairly distinct things. A lot of times they're confused in many designs and in many contexts where people talk about macros, but they're really very different things. List here some examples of what macros are used for. So they're, these are very familiar things. Macros are being used in the real world, for better or worse. Now, they also seem to have a really bad reputation, and this reputation seems to go quite a ways back. This is a quote from the paper by Steele and Gabriel on the history of Lisp, and it's talking about different proposals for macros in the context of Lisp and how they were viewed at that time. Now, things really don't seem to, the question that one should ask now at this point is, have things really changed since then? And it's not clear that, for the most part, things have changed very much since then. But I think that there are positive developments that are going on that can improve the situation.
So we have type-safe macros now in some assemblies? Things that actually you can type, like you can type a programming language? I'm thinking of the stuff that Schwarzbach and colleagues did in the context of the Big Wig project.
I don't know about that stuff. So that's something that I have to find out about. Yeah. Do you want to?
Are you going to go over related work, or?
I will mention related work at the end.
Okay, because you were sort of. This seemed almost a place where you were going to do that. So I was wondering.
No, I'll mention the related work at the end.
We've had some work, right? since the early days.
Yeah, I happen to not know about that word. So
Well, I mean, the hygienic stuff. I mean, there's hygienic macros.
Sure. That's right. There's certainly been things that have happened.
Right.
But overall, by and large, the stigma still exists, with respect to macros.
Yeah, I mean, we still have C and the C preprocessing.
And it's not clear that there are sort of proposals that are coming out that are winning in terms of the pool of proposals for macrosystems. But that's certainly some reference. The reference you mentioned I wasn't aware of, and I would like to get that from you after the talk. So a lot of times what happens with macros is two things tend to happen. A lot of times they're viewed as either an implementation detail. We don't need to worry about them. Don't need to take them seriously at the level of language design. They don't have to be part of the spec of the language. We don't have to say very much about them formally. And one of the views that kind of explains this attitude is that sometimes they're viewed as just hints to the compiler. So in common Lisp, for example, there's no guarantee that macros will be expanded. And in fact, you are asked to not expect that they will be expanded and not depend on that. Okay? The other thing that happens a lot of times is that they're often viewed as, they're an ad hoc kind of a not very well thought out way of doing things, right? And these two things are not. I don't agree with these two points of view, and in particular, if we insist on taking the view that macros should be just hints to the compiler, that the programmer is not guaranteed that something will be inlined when you add this inline pragma, then they're not going to be used, because if the programmer needs something to be inlined, they're going to go and inline it themselves, and you're going to end up with a lot of code duplication and bloat in your code and all kinds of problems because of that. But if they're just hints, that they're not going to be used. They're not going to be achieving the filling the role that's required from them from the programmer's point of view. The other thing is that we don't really, if we're managers leading a team of programmers, we don't really want to discourage them from using macros or a good macro system, because that has disadvantages. You end up with very unstructured code when you could have had much better code to start with. So how do we go about designing macros? Well, there's really a lot of different proposals out there. Python has like several variants of Python that support different ways of doing macros for C, for example. And almost every language has a lot of interesting proposals. But the tendency seems to be that the goals are mixed. Are we doing it for performance, to have control over what stage things or what time things are done at, or are we doing it to enhance the expressivity of our language? Now, these things are often mixed, but it's worth asking the question, are macros really the right way to try to enhance the expressivity of a language? And my feeling about this question is that no. If we want to talk about enhancing expressivity of the language, then we should focus on things like, first of all, the syntax, and then other things like the type system, for example, that might be, stopping us from writing certain programs that we would like to write. So I view macros primarily as a means for getting a better handle on performance and when things done in the execution of the program. Okay.
So you don't see this DSL approach as sort of a rationale for?
Well, I do actually, and so the DSL, when you use macros to implement DSLs, you could have implemented the DSL without the macros, but the macros make your implementation more efficient.
But
Okay.
I also see it as a way of introducing new language abstractions without all the overhead of creating a new type system, proving its sound, developing the language. I mean, in some sense, if you can encode your abstractions in the current type system through basically a macro compilation, then it's a much lighter and faster way for you to invent a new language abstraction, especially if the macro, if there's syntactic support for doing things like infix and et cetera.
So I almost agree completely, but there's a small or big small print with this agreement, and that things like infix and distfix operators, they don't have to have anything to do with macros. Okay, they can be supported by a language without having macros at all. They can have, be supported in a language that's a single stage language, no macro expansion. And a lot of these features are, lumped, of things that we call macros are lumped together. And so what I'm going to do here in this talk, at least, I'm going to say, okay, well, the only things that I'm concerned about, the only feature of macros that I'm concerned about modeling is the separation in phase that they provide. Okay, but a lot of the other features that you mentioned, they should be things that I can implement in a language that gets executed in a single stage. All right. So if we're concerned primarily with the separation in stages, and we see that as the primary mechanism for getting rid of this overhead, abstraction overhead, that Tom mentioned in the context of implementing domain-specific languages, for example, then one of the things that we would like to do, one of the most basic things that we would like to do, is to have a guarantee, for example, that when I say that something is a macro that needs to be inlined or unfolded at a certain point in time, I want to be guaranteed that this will happen. Otherwise, this will not, the program will not deliver the performance characteristics that I wanted from this DSL implementation. So if I want guarantees, if I want to know exactly ahead of time, have a clear specification of what the macro system will be doing, this is really a question of semantics. So how do we define the semantics of macros? Well, there's a lot of work that has been done, but really, from my point of view, one of the most interesting things that after the work on hygiene in Scheme was the work in Shell's Scheme, where there's this macro system that allows you to essentially have macros that generate code, but you're not allowed to inspect the result in general. And the semantics is actually defined for this language, is actually, the semantics for the macro part of this language is defined in a fairly good deal of detail. But the way it's done is essentially a mixture of what looks like big step semantics and denotation semantics with gensym on the side. Okay? So it's a stateful, implicitly a monadic semantics, where we have to thread through this generator of names. Okay, so this is really something that's very close to what we would like to have, but it's still a very complicated basis for reasoning about macro languages. Okay, so what we're going to try to do is to try to find the simplest possible way of defining macros using what's available today. All right, and our approach specifically is going to be to try to give macros semantics using taking advantage of multi-stage languages. So essentially, we'll give macros semantics by translating them into multi-stage programs. Okay, and the basic idea is to take advantage of all the results, variety of different results that people were able to get on multi-stage programming languages. Now, one of the things that happens here, if we try to take this approach, is that we can't really define all the things that people refer to as macros. So in general, for example, we won't be, this is not going to help us in dealing with all the parsing extensions that macros are sometimes used to do. We're also not going to have macros or a macro system that allows us to generate some code and then go and transform it later. Okay. A lot of people think that that's a very important thing to do, being able to generate code and then transform it. But I happen to actually, based on my experience, think that that's not necessarily a good thing to do when you're implementing things, even like domain-specific optimizations. There are other much more structured alternatives to implementing things like domain-specific optimizations. Yeah.
So the first thing you mentioned was parsing.
Yeah, like infix and distfix operators, for example, and so on. This part here about giving macros a semantics by translation into multi-stage language is not going to deal with things like the grammatical extensions that a macro facility would give to your language.
Like redefining open brace as big
begin and end braces.
Yeah.
But for example,
Sorry, I'm not a language guy.
We'll see. That's okay. We'll see examples. I mean, I try to actually put much more examples here than technical.
Between transformation and generation, let's take an example, something like setf in Lisp. Which side of the world does setf fall on?
What does setf do?
setf allows you to, for example, you can say setf the car of x to be quote A. So it transforms into a replaca.
It transforms the. Is it, like, for example, one of the things that I remember that
it allows you to have something like L-valued expressions. You add those language, so you can say setf, some property of something that looks like a call, and you sort of then transform it to some value, and depending upon what that thing is, you can and there's some extension mechanism, so you can then turn this into a direct call to do the set, because you don't really have L values as values in Lisp.
I'm not sure of.
Okay, fine. Well,
you can argue that.
Okay, if you don't know setf,
I'll use some concrete examples to illustrate exactly what this language does, right? So, sorry, you wanted to say something?
I think you can argue that setf is generative in nature. It's just filling in the right thing versus this thing that Waleed seems to be worried about, which is that, if you actually wanted to take that and generate code with it and have other macros, then processing.
Right. So syntax case. Is that syntax case scheme is intentional?
Is the thing that you generate then required not to be a macro? You don't have successive sort of processing, because that's clearly you can do that in Lisp.
You can have macros that use other macros, and the expansion can be nested. But you can't have a macro that would expand and then another function that would look at the result of the expansion as an S expression and do arbitrary computations on it. Okay.
Inspection, I mean, macros are usually parameterized by other things, right? Can the macro inspect? I think this was John's question. Can it inspect when you're handing it?
Yes. This is like a fexpr, the thing that you were describing?
But this is a little different.
Okay.
But fexpr is another example of the kind of thing.
Okay. So fexpr, I wouldn't do fexprs. Yeah.
You can inspect the.
That's right. This language wouldn't. Cannot. Yes. That's
so
right.
I think that's.
Oh, it can.
So fexprs I know because Mitch One had a paper about them, and I looked at the semantics of that in detail. Good. All right. So we do lose some expressivity with this approach, but then again, this is very similar to the way whenever we try to use a type system or an analysis to get a guarantee about the programs that we're looking at, we throw away some of the things. All right. But the class that we get is still interesting. So the rest of the talk, I'm going to look at some examples of the macros that I can express in this language, a little bit about the basics of multi-stage programming, which are fairly simple. I mean, the big part of the point about these things is that they're very straightforward, and it seems that there are a lot of people here that know about schemes, so that should make things much easier. And then we'll look at the translation, macros as multi-stage programs, discuss some of the related work. There's a lot of related work. I mentioned only some of it here, and go to the conclusions. So here's MacroML, which is a toy language that has only been designed in a paper and implemented in a very sort of simple, basic interpreter way. So this has a syntax very much like that of SML of New Jersey. So instead of saying let fun or let val word size is equal to this term, what we would say is we would use this keyword mac. So this would be the macro. And the idea is that in this expression below, before we do any evaluation on the program as a whole, we have this term inlined here. Okay? So this is a simple way to introduce syntax for macros in a language like SML with a well-defined semantics. Right? Now, one of the interesting issues in designing such a language that comes up is if we make such an extension, then we immediately lose, in this particular manner, then we immediately lose one of the basic properties in call-by-value languages, which is that we can treat any variable as a value. In this case, word size is not a value. So if we do a substitution where we assume that it's a value and it disappears, then this, or duplicate it, then we would be duplicating an effect. Okay. So in fact, even though this looks like a straightforward thing to do in terms of introducing macros to the language, it's a bad design choice. Does that make sense? So here, introducing macros like this would mean that we have things that look like variables, but they're not values. And that would be problematic. That would affect the properties that we would like to have for the language as a whole. So the solution for this case, this is the simplest kind of macro that we will allow, which is inlining, is to make sure that whenever we want to define a macro, it looks like a computation. That takes care of that problem. Okay?
But presumably you can also take word size and simply pass it as argument to functions and so on.
You can pass it, you can use it in other macros.
Can you call a function with word size as an argument, and then you bind that to a formal x, and then you call x?
In that case, it would be expanded before it's passed.
Really, even if it's not being called there?
I'm sorry. If you take it as an argument, it would be just an argument. And then at the application side, if you use...
Then you can apply it, and then it gets...
Yeah, yeah.
Okay, so it's just like a function in that case.
The other term that you constructed is just a function. But the word size is always expanded in the free occurrences of the term word size in your program are always expanded.
So word size cannot occur without an argument to apply it to, in this case, unit.
That's right. That's right. That's exactly right. So one of the things that the type system is going to do is it's going to make sure that whenever you use word size or any macro, it's going to be fully applied. Okay?
Can't even be curry, nothing like that.
That's absolutely right. It's a different beast. And the type system makes sure that you only use it in the way that it's intended to be used.
So, for example, you can't put it into a data structure. You can't apply it to a...
That's absolutely right. It's something that's there in an earlier stage, and it's supposed to disappear completely. That's one of the things you want to be guaranteed is going to happen. It gets done early. And, in fact, it turns out that you don't even need a full type system to do that. You kind of just need an arity system. And that's nice because it means you can define the whole operational semantics in the untyped setting. Okay.
So it's like a function, but the function is called at the time the text is parsed.
The function can't...
That's right. Essentially, you parse it, and then you do certain operations that are completely well-defined by semantics that I can fit on a page for the small calculus that I'm going to present. And then the result is what gets handed over to the compiler.
And then if it hasn't disappeared, then that's an error.
That's right. The next thing, first thing was inlining. The next thing is parameterized macros, which is the natural extension. It would allow us to do things like this in a function language, define things like delay enforce, not delay enforce, like that.
It's your Southern accent.
So we use the $sign for delay and the question mark for force, which I think was used by some papers by Kursal Kasaki. And the macro says delay of E is just E with a lambda abstraction around it with a dummy variable, and force just applies this term. Now, of course, we can't define these things as functions. We strictly have to have them as macros and have to make sure that these things get done early, right? So if we're not guaranteed that the macro gets unfolded at an earlier stage, then we don't know if we're implementing delay and force correctly or not. Confuse call by name and call by value semantics. So these things, a term like this, for example, would simply expand here. Now this is kind of a nice opportunity also to note that this X always gets renamed because all the bound variables where I might be substituting something over them in the macro definition, they get renamed so that we don't have the possibility of variable capture. Any questions about this? Or okay? Previous one. Okay. So another thing that we want to do in general is to have kind of much more work be done at expansion time, more than just functional inlining or simple inlining of constant terms. So for example, we might have a term like this function declaration here for power, which is a standard example from partial evaluation, a classic example. And what we want to do is we have this application here, and we want to compute 2 times 3 during expansion time and invoke power as a macro. So that, in a sense, we get this definition unfolded. Now, we can certainly replace fun by Mac, and that would be a well-formed program, But that doesn't give us the behavior that we want. Do you guys have any, does anybody have any idea what happens here?
Just substitute those expressions, the parenthesized expressions, into the body of the macro.
And it doesn't do it once. It keeps doing it over and over and over again. Because this is a recursive macro, and it has a use of reference to itself in the body. So it diverges.
Oh, right, because it evaluates 0.
That's right. So that's right. The if becomes just completely part of what it expands to. So what we really want to do here, and there's no easy way around this except to be explicit about what is going to be an expansion time parameter and what's going to be a second stage parameter. Right? If we don't make a distinction explicit, then things get very confusing from the point of view of the semantics. And then here, we're also going to say, well, I don't want you to just generate this if. I want you to execute this if at a macro expansion time. So this escape is essentially like a comma, something that performs a computation early. So I get to do the test at expansion time. Now, what I return is not going to be the literal one. It's going to be the piece of code one or a quoted one. That's what the brackets do here. And here, I also have to return a piece of code because the result of expansion is always a piece of code or a syntax tree. With a delayed multiplication, and I've included the x here, and I make recursively a call to power with the parameter n-1 and x. And then I also indicate here which parameters I want to have performed early and which parameters I want to have late. So the result of that gives me something like this. Right? Notice the 5 plus 6 doesn't get performed and the multiplications don't get performed because the way I wrote the program here tells me, well, I want to keep all of these things for the second stage.
In this case, 5 plus 6 gets evaluated 6 times, which is not a problem. But if you had side effects, you could have given the macros or this kind of once.
Different semantics. So
if you would want the semantics, you could have.
So what you'd want to do, you'd actually introduce a binding for the 5 plus 6. What's that? You can write this around. So the way in this macro system, this is essentially we finished 3/4 of the functionality that this macro system gives you, and the rest, like what you're saying about not duplicating 5 plus 6, you can do by saying surrounding this call, for example, by something that says let x equals 5 plus 6 in pow twiddle 2 times 3 of x.
But if you want to get the same semantics as if you use front instead of back, then you have to go to extra work to do that.
Yes.
Fine.
Yes.
So do you need to put the twiddle in all those different places? I see it on the actual argument to the macro. I see it on the parameter to the macro. I see it in the recursive call to the macro. So that's necessary. So both the formal and the actual.
For what?
Auto-twiddlification.
So all of these appear to be, this is a little bit surprising because most other macro systems, let you get away with all kinds of little versions here and there and guessing based on different heuristics. But if you want to have a straightforward translation into something that is explicit about when things get done, this seems to be the smallest set, or a minimal set that of annotations that you can get away with. Right? There are a few alternatives. It's not. I don't think it's canonical in a sense, but that seems to be pretty small. And it's hard to see how you would get less annotations without depending on a type system, for example. And here we're trying to define an untyped language which any type system can be placed on top of.
Can I just ask one question here also? In a language like Lisp, if you wanted to do this kind of thing, what you would do would be to have a macro call power which would look at the first argument. Say, for example, is it an integer? If so, then do the expansion. Or is it something that it can evaluate to an integer? So, but you don't have that kind of inspection. Instead, you use simply evaluation at the previous stage in order to achieve that.
That's right. So the basic mechanism doesn't do that. But because you have things like data types, for example, right, where you can express all kinds of stuff, as in, an early stage value and a late stage value, then you can say early and, data type either of alpha is an early alpha or a late code of alpha. All right? So we cut everything down to the bare minimum, and you can actually do essentially the same things that you could do before, but you have to be more explicit about it. And you're not forced to have a runtime overhead with the basic macro system. So the last thing, which was kind of the most interesting thing for me, is this ability to define binding constructs, macros that introduce new binding constructs. And essentially the way this would be done is, let's say I want to define a new kind of let statement. You know, there's in SML there's let val, let fun, and I want to define my own let opt, which is a particular kind of let statement. What it does is, when I write let opt x equals E1 and E2, what I want this to be expanded to is case E1 of just x, return E2. And if you have nothing, then just don't do anything. All right? So this is a simple example of a monadic let statement, kind of an explicit sequencing operation. So we actually used this kind of syntax when we first introduced these macros. But in fact, this is not a really good way of good syntax for doing this kind of thing. And the reason is it doesn't make a lot of difference here. In fact, this almost looks like the way if I wanted to define a let statement in terms of lambda and application. This would be pretty much, I would just write, lambda funx go dot E1 or dot E2 applied to E1. It's almost like how people write it mathematically, syntactic sugar mathematically in papers. Okay? But in fact, that's not, from the programming point of view, there's a really annoying property here, which is that this x here, which normally would only have the scope here, E2, right? It doesn't have this property here, because this x has to be exactly the same as this x over there. So there's a very funny scoping situation in this notation. In particular, if I just happen to be looking at this part of the code here, and I say, oh, well, this x is clearly not, x is a variable and E2 is a variable. And clearly x2 is not used in E2. X is not used in E2. So I'll just write underscore here. Okay? That would actually create a problem for the semantics of this language. So what we have to do is we have to split the connection explicitly between this x that appears in the pattern and the x that occurs in the term that implements the pattern. So the way that this would be done is by an idea that's taken from, well, most recently higher order syntax, and before that from the way Church used to encode binding constructs in the lambda calculus. And what we'd do is we'd say, okay, this x here is something that occurs free in E2, and the way we indicate that is we make an explicit association here. All right? So this notation here, going from this simply E2 to twiddle E2 of bracket x, says that this x occurs free in this term E2. And then when we use this x here, then we explicitly say what free variable is being passed or is going to occur in E2. So now, if I look at just this piece of code here, then I would know, oh, this x is clearly used here. If I want to rename this to y, I have to rename this to y too. I just follow the same naming conventions. Okay.
And the macro that generates the result of this will basically pick whatever the name of the free variable is that occurs in E2 and use that.
That's exactly right. X doesn't have to be the particular name. It doesn't have to be called X. This will denote whatever name is used in the source program. And in fact, what it does is it'll give it a fresh name again, but the correspondence will be there. Okay. So certainly this matches any name that's used in the binding construct at that point. Okay. All right. So that's basically what the calculus does. And these are essentially the main kinds of things that we think are safe to use and would avoid a lot of the problems that a lot of the macro systems in the past have had. So just to be clear about what, we've presented macro ML, what are the multi-stage programming constructs? The basic idea is that all variables, whether they're inside quotations or brackets or outside, they're statically scoped. Everything has a static distance coordinate, even though some things get done before others. What we want to do in general is with sorry, did you have your hand up?
Yeah, I have a question about the higher order map syntax that you use. So does it require a user of the macro to do anything special in terms of the part that appears after the
No. So the user of the macro would just write let opt x equals 17 in x plus x.
Okay.
Right, so it's just...
he doesn't have to explicitly abstract all the variables.
That's right. This is just in the definition to make sure that the definition enjoys alpha conversion or doesn't...
Generate that automatically, basically, sort of do header matching.
Yep. The application of this would be simply, something like this, where E1 and E2 are instantiated to arbitrary expressions, and X is... and the way we abstract away, by the way, here from the parsing issue is here we're restricting ourselves to an existing binding construct, which is let. So we follow the structure of an existing binding construct and say we sort of let val, we have let fun, and so on. Okay. And as I was saying earlier, the parsing is going to be a separate thing. So multi-stage languages, the way to think about them is that they try to do better than strings or data types parse trees in terms of the guarantees that they provide about generated programs. So when we want to have a quotation mechanism of some sort, strings give us some basic guarantees. Using a parse tree gives us slightly better guarantees. And the main thing that we were concerned about in multi-stage languages in general for most of the time is static typing and making sure that before we do the expansion, we can guarantee that whatever expansion produces, it's going to be well typed. So in some sense, it's early type checking. So if you're wondering what's the difference between multi-stage programming constructs and quasi-quotations, it's all in the typing and the implicit gensim for binding constructs.
The typing guarantees termination?
No.
So do you have a way to guarantee termination?
Nope. Not anything better than what people who guarantee termination have. Okay. In fact, what you would use is exactly standard termination analysis to do that. Yeah. Here's what they look like. Quotations, they would evaluate a term like this to essentially itself. Anti-quotation would allow us to include things that were defined before or computed before into a bigger context. And this run construct executes the term that we have and gives us the result. These are all the constructs that we have in a multi-stage language. In terms of typing, it's fairly straightforward. If I have a term code of X, it'll have the type code of T, where T is the type of X. Twiddle kind of works in the opposite way. And naively, we can think of run as essentially doing the same thing. But in practice, the devil is in the details here. And that's most of where the research goes. But that's not very relevant to us.
So do you worry about the side effects of the things you run?
It depends on what effects. So if we have termination, then it's in the untyped setting. You can define your semantics to tell you exactly when effects occur and whether they're duplicated. Type safety becomes tricky if you have side effects with references in the first stage. If you have a purely functional language, it can be easy. If you have a functional language where if you have an imperative language where you don't allow people to store pieces of code in a global state, that also keeps things easy. All right? But if you start taking pieces of code outside of their scope and putting them in state, it's very hard to enforce the static scoping principle. All right? So work that's been done in the past on multi-stage languages includes things like ensuring that type safety, and a lot of the work, as I mentioned, was on the type safety for the run construct. And also, somewhat relevant to the talk today, or the results that I mentioned today, are the fact that they have strong equational theories where not only do I know that I can use equational reasoning on first stage computations, but I also know that I can apply the equational principles on whatever I generate, and it's still sound. And the reason I can do that is because I don't inspect the stuff that I don't allow my programs to inspect what I generate. Okay. There's a lot of stuff also that I'm not going to be, talking about here today. So back to macros. There were two kind of relevant pieces of work that we did here. The first one was to develop a type system for the language, or a variant of the language that I presented by some of the examples here, and then define a translation from the typing judgments of this language into typing judgments for a particular multi-stage programming language. So what this translation from typing judgment to typing judgment does is it both gives me a semantics for my macro language, because I can forget the typing information and run my multi-stage program, and I know how to do that. It also gives me a type safety result, because I know that all my translated programs are well-typed multi-stage programs, so I just inherit that safety result right away. Okay. So this was the first thing that we had done there, and it was mostly done for a language very similar to the one covered by the examples. More recently, what we were able to do, which in a sense is more elegant, is to give a translation from the untyped macro ML language, or a variant, slight generalization of the untyped macro ML language, to untyped multi-stage programs. And then separately show that well-typed terms map to well-typed terms as well. And the nice thing about this is that this is something that can be reused for any type system. Okay. And we also know that we get the equational properties at the untyped level for multi-stage languages, and so the macro language also inherits these properties directly. So the formalized version of the language, I'm going to try to go over that quickly. Basically, a mechanism that we use to capture the idea of arity for a macro is as follows. This is a late stage parameter. So these are kind of patterns that can be used as arguments for macros. So this would be a late stage parameter. This would be an early stage parameter. So remember in the power example we had twiddle n followed by an x. Right? So those are the two examples here. If I have simply a couple of parameters, I put them in a pair. And if I have a parameter with a binding construct, as in the case of let, for example, then I would say I have a lambda x dot p. All right? So this allows me in my calculus to formalize the notion of arity, or the notion of patterns. And from that, I can extract in a fairly straightforward way a notion of arity that's going to be important in the development of the untyped language. In the terms I have standard, in fact, up until here, standard lambda terms. I have this little gadget here, which we haven't seen before, and this is essentially a first-order macro. Okay, so this is a kind of a lambda abstraction, but it takes a pattern, and pattern matches against it, and then executes this in the scope of the bindings here. This is a macro application, and what a macro application needs that you don't have in a regular application is the arity. And like somebody was asking earlier, what if I only partially apply my macro with respect to the arguments that it takes? That would be a runtime error at expansion time. And a good type system for this language would exclude this kind of problem. And it turns out, in fact, that it's even simpler than a type system. You only need an arity system checker that'll take care of that. And then finally, I have the macro declarations. And as we noted, it would have been nice if we could hide these things and just say we don't use any of the multi-stage language constructs explicitly. But it turns out, in order to have recursive macros, you really want to be able to distinguish between when a particular if statement in the recursive definition gets performed and when not. Okay? Yes?
So I didn't quite understand the pattern. Can you explain that again?
These here?
No. Yeah, that one. Yeah.
This? So this is essentially sort of representing a macro without the name. So this is a recursive definition of a macro. So this would have the same functionality as this definition here, but without the name. So it can be passed around.
They can be passed around. Well, so this is confusing because earlier I think that John's question was, are these macros first class? Can you pass them?
So they can.
So your answer was no.
Yeah. So what this does is it's kind of a technical mechanism that the programmer doesn't necessarily have to be exposed to. So it's this extra thing that's added into the calculus for convenience. I can't remember right now whether there were good reasons to actually use it in the language or not. But the main mechanism for defining macros was the let mac.
I mean, because if you have it this way, I mean, this allows you to define a macro and then you need to apply it.
Basically.
But unless you have unless terms or variable bindings in the language are actually allow you to be bound against macros. So, for example, the lambda x.e, maybe I can bind.
Let's look at the reductions. Let's look at the reductions, and we'll see.
But I was just trying to understand what the language can and cannot do. And
Well, let's look at
conflicting messages so far. You've said for earlier on that macros are not first-class values, and now you're saying they are.
Well, it depends on what you mean by first-class values.
That is,
So
I can have a
this
lambda.x term, okay, which is in
Let
the,
him
in the
explain
second.
now.
Well,
What's that?
No, I mean, he's explained twice, and I don't understand because he's conflicting himself. So lambda x.e, okay, is a term in the language, right? What,
Yes.
Can x range over macros?
In the untyped setting, yes.
Okay, so you're making a distinction between what we saw earlier, which was typed, and now it's untyped, and now you increased expressiveness.
This is the calculus. The examples are to illustrate basically what letmac would let you do. Okay, this, as I said, is a technical device that was introduced for convenience in defining the semantics. As you pointed out, as you noted, you can write one of these applications with an explicit macro here, and that's probably why we introduced this thing, so that our calculus has substitutivity and it's easier to work with. Okay, but when I think about the language, I didn't really have a use for something like this. All right, and I don't think that you can do. Maybe there are interesting things that you can do in this calculus that I hadn't thought about. That may very well be. Okay.
So question. So what are your constructors? Pairs?
Right. That's right. I have only pairs and lambdas, pairs, and projections from pairs.
So I wonder about it, coming back to the termination. Why don't you just enforce sort of that you only decrease type size as you go now? It's
So do you know
a fairly
how-
natural thing for macros. Why do you want to actually increase?
So if you want to do termination analysis, you know how, like in SLAM, you just black out certain things and then you refine part of your program? Basically what you would do is you take your multi-stage program and essentially black out the stuff in quotations, except for the escapes inside. All right? And you do completely standard termination analysis.
No. I mean, why do you want to have, I guess, a Turing-complete macro language?
If you want to specialize something like the power function, if you find yourself writing power of 17 by hand and power of 42 by hand, you'd be spelling out all these things in detail, but you can generate them in 3 lines.
Well, the alternative would be if you could match only over sort of inductive data types rather than integers, right? Then I could build up my little piano encoding 17.
I see.
And then the macro would only work over that, and then you could
it'd be
prove
very
termination that way, right?
Okay, I see. So you're going to have these base types, and you're actually going to at macro expansion time allow multiplication, addition, and all these reductions. Yeah. Okay. Forget it.
Okay? All right. I mean, there are certainly, I can see reasons why it would be nice to have a terminating first stage. I would fit that on top of this. Okay? With standard termination analysis. This is just the mapping from the patterns to the arities. The semantics is going to use these 2 functions, scope and phi, which basically, scope, what it's going to do is, for any variable that occurs inside a pattern, it's going to go fishing for the environment that this variable occurs in. And by environment, we simply mean essentially the lambdas that we have to go through to find this variable. Okay? That's the first function. And the other function is going to essentially also take a variable and a pattern and tell us the path inside this pattern for this variable. And so what the phi is going to be useful for is all our functions are going to be implemented, all of these different arity functions, they're all going to be implemented by functions that take 1 argument that has everything lumped in it. So the phi function, what it's going to do is it's going to tell us exactly how to fish out from that value that we get at runtime, the particular thing that corresponds to this value in a pattern. So there's almost intuitively kind of standard pattern semantics. Okay? The interesting thing that's happening is we have patterns with these binders in them. The main part of the translation maps a letmac that looks like this into an escaped expression. This means that the whole thing are terms when they're being translated at level 1, we assume that we're in a delayed context. Okay? We have everything everything is delayed because we're at pre-processing time, not at compile time. So by default, our program is just delayed. It's not really executed. And then we have the macro is mapped to a function declaration, where the first thing we do is we fish out basically the various parameters that occur in the pattern using this phi and scope functions that I presented in the previous slide. And then we return a piece of code which is just a translation of this E1. So here it's completely compositional. And again, this is just E2. And VIs, as I said, are simply the patterns, the variables in the pattern up here. Okay. So this is the main construct in this language. The whole semantics for the language, the calculus, is here. Okay. We don't have to go through all of the different constructs in the semantics, but basically these up until this point, these are auxiliary definitions. If we want to look at how an application of a macro is done, well, first actually somebody pointed out that we have this construct that's the first order macros. They're basically translated into a lambda abstraction where we take the argument and again simply fish out the values that are in this pattern and use them in X. Okay? One of the things to note here is that this pattern can only occur at level 0, not at level 1, unlike the letmac declaration. A function application is done similarly. It occurs at level 1 and is escaped, and the first argument is translated in a straightforward way. The second argument itself has to be translated in a way that depends on the arity, and that's essentially where we need the arity information in the translation to get it right. Okay. The most important thing about these rules, I mean, we don't want to go through all of them right now, is that it's a compositional translation, and there's no gensim anywhere. All the freshness, all the gensimming is essentially something that we inherit for free from the underlying multi-stage language. And so once we're satisfied, we have results from somebody else that tells us the multi-stage language satisfies equational properties and so on. We can treat this as a semantics that has no state in it. That's already taken care of for us. Okay. The reductions with this translation, we can extract from the reduction semantics for the multi-stage language or the equation theory these reductions for the new language that we've defined. Lambda application, fortunately, does what you expect it to be doing. The constraint here, the superscript 0, well, first we have E and V, that's for the call-by-value semantics. The constraint here simply says that there are no escapes. So if it's an E1, it can contain escapes. E0 means first get rid of all the escapes there, and then you can do the beta. Okay. The letric is also standard. The application of a first-class macro is done only when the pattern that I have in the lambda matches the signature that I have indicated at the application site. All right? And then in that case, it's done in this manner, where I substitute this into the V into the body of E1, fishing out all the things that need to be fished out from there. And escapes are, this is a standard rule for escape. And then I have all these reduction semantics that give you standard or the kind of equational properties that you'd expect from a let macro declaration. Right? And the idea, again, is that with this approach of giving a semantics to the macro language by translation to the multi-stage calculus, we can derive these equations and verify them fairly straightforwardly. Okay. Related work, mentioned Lisp quasi-quotes and the issues with the common Lisp macros. Also share scheme, and I think we discussed briefly, people mentioned the C preprocessor. I mean, I'm sure everybody here is familiar with the system by Weiss and Crew, but I was curious what the status of this is now.
It was put away as soon as the paper went not used again, to the best of my knowledge.
We've been learning tremendous amount of stuff because we have this meta-OCaml implementation of a multi-stage language. And it's a real shame. I mean, you really need to have a lot of experience with these designs to find out whether it was, it was something that could work in practice or not. Okay. C++ templates seems to be one of the most successful template mechanisms, at least in terms of widespread use. It's very strangely designed, not really designed as in the way you'd expect a macro system to be designed. It is Turing complete, which wasn't designed to be. So maybe you should just keep this Turing analysis or termination analysis separate after all. There's an interesting paper at Uppsala, 2001, by Jonathan Bachrach and Keith Playford for a proposal for macro system for Java that has very much inspired by Scheme, and in many ways, very, very close to Scheme. Also shares a lot of the design choices with template Haskell, which was developed by Tim and Simon Peyton-Jones. I was just looking at this paper recently, and one of the most interesting things is that at the end of the paper, they really say that it's very hard to get macros to work in this system. And despite the fact that they've built support for debugging macros and helping you figure out what went wrong after you've generated something and then it doesn't work and then you want to go back, they still say it's very hard to debug macros and get them to work. And at the end of the paper, they say, well, the main piece of future work that they'd like to do is to have more guarantees. And I thought that was actually kind of a nice thing to hear, because that's essentially the approach that we're taking, is trying to make sure that you can get the guarantees as you're designing the language, and not jump too far into working with plain parse trees and try to recover the properties after the fact. Also related, but I'm not sure exactly how this is related, is the work on extensible grammars by Cardelli et al. And I have to say, I haven't looked at this work for a while. I know it does focus on parsing, or parsing issues more than staging issues. But I would like to look back at it and see exactly what the relation between this kind of work and the kind of the macro calculi that I just presented today. Calculus, sorry. Other work that comes up and seems to be related, which is the meta-object and aspect-oriented programming stuff. There seems to be sometimes a little bit of inlining and macro-like stuff there, but a lot of times it seems that what they're doing is more semantic modifications to the language than modifications at sort of preprocessor style modifications. Conclusions. We're able to, using this approach, we're able to give very simple semantics, very clear semantics to a macro language. The specs are very clear, and they're useful in the sense that you can directly use them to prove things like type safety, develop a type system, prove type safety for the type system, and even derive equational properties that are, and then prove that they're correct for this language. We think that this is a good sign from the multi-stage programming languages point of view. Of course, you do lose some expressivity. You don't have these transformational macros. If you want to, another thing that you would lose is the ability to have delayed type checking and try to circumvent the type system using macros. Both of these things are things that people sometimes value in a macro system, but I think that macros are the wrong way to achieve these. To achieve this goal in particular. And for the transformation part, they're also much more systematic and much more promising alternatives than just doing program transformation after generation. Thank you.
So, how hard is it in the sense of what's going to go wrong if we take these ideas and try to implement them in a language like Java or C#?
So, the main thing that I see, one of the first things that I see actually, is this focuses, the lambda calculus is a completely computational language. Okay, you don't have declarations. simply have expressions. You don't even have statements. So there's a lot of syntactic stuff that has to be taken care of to deal with the different syntactic categories that correspond to expressions and statements. And then with declarations, we'll probably find that there are different kinds of things that we want to do and want to explore that don't have a direct correspondence to a lot of these things, basically the staging, but rather more with using different type systems and possibly more expressive type systems for being able to say, I'll take as input some data or some metadata and produce some class declarations out of that, or the equivalent of a class declaration. One of the things that I'd really like to know is if a framework, a calculus can be defined, toy cut down version of one of these languages, where you can really separate the idea of generalizing the expressivity of classes and making them be dependent, allow them to be dependent on values, and have that be very separate from generating actual files that contain the text of specific generated classes.
So one of the things that strikes me is, one of the challenges with macros is it's a difficult reasoning. It's difficult for the program to reason about the meaning of the program, right? There's sort of two stages now. You have to actually, in your mind, execute what the macro is going to do when it gets expanded early on, and then the resulting code, which you never see, is code that will execute runtime that has some semantics. So how do you connect? One of the reasons people use, I think, macros in Lisp, say, for language extension is because, static, for example, it tries to simplify the semantics of some other Lisp constructs by unifying the assignment operator, essentially. So, so you can see where you don't have to really know how setf works to use it. Do you see the same thing happening with the kind of macros that you're describing?
The setf part, I think that it's one of these many nice things or convenient things that Lisp does for you that is orthogonal to what I view as this, simple notion of staging that, as far as I can tell, is orthogonal to all kinds of other concepts that come up in programming languages. So, out of motivation for orthogonality in design or language features. I like the simplicity of what we get from this, and the fact that most of the time, whenever we try to mix it with other things, like more advanced type systems, for example, these things don't interfere; they work well together. At least in the functional setting. So in the imperative setting, you have to be careful about, for example, computations in the first stage. If you want to be aggressive the way we do in Meta-OCaml or typical multi-stage languages and say, I want everything to be code to be a first-class value, which is definitely the case in a multi-stage language, then you want to also store pieces of code. But if you want to say, okay, well, I'm only going to allow real C# computations that I could do before in the first stage, then there's no problem. It's only a problem when you also want to store pieces of code or fragments of things that you're expanding into in the first stage that you start having tricky issues to deal with at the typing level. I'm not sure about the first part of the question.
We can talk later.
Yeah.
Any other questions? Thank you, Mr. Maker.
Thank you very much.